So thank you very much to the OGS and the Planning Committee for inviting us here today to talk about this program. So this program has been ongoing since 2013. It's a study in Eastern Ontario, and we've been talking a lot about Eastern Ontario today, so that's also pretty exciting. It's a study in Eastern Ontario that we've been working on, and it's a program to support development planning, and specifically the development of an aquifer capability screening tool. So, there's slides up there. In Ontario, it's the responsibility of the municipality to ensure that before any new lot is created for development, that lot can be safely serviced. So, if you're in an area, in a rural area that has no municipal water line, you're going to be depending on your water servicing from private wells. When we look at private wells suitability for development, we are going to be looking at guideline D55 in Ontario, and the City of Ottawa developed our own guidelines, which is clarification of the application of D55 in Ottawa, and we developed those guidelines in 2021. So the issue we have, and I guess when we look at water servicing, we look at two main things. The first one is water quantity. Do we have enough water to supply that proposed development? And number two is water quality. For water quality, we look both at health-related standards and aesthetic-related standards where there's a published maximum concentration considered reasonably treatable. If you exceed any of those values, if you have a health-related standard or you exceed the MCCRT, then the municipality will not support development. The issue we have in Eastern Ontario is that we have areas where there's naturally poor groundwater quality, and that's the function of the geology in the area. One of the main issues we see is we have a remnant post-Champlain Sea, Champlain Sea water trapped below thick layers of clay. And so you actually drill wells down and find remnant seawater. We also have issues with highly mineralized water from our shale aquifers. The issue we've had in Eastern Ontario is that a developer will buy a plot of land with the intent to develop it with a subdivision on private wells. They'll start spending money drilling wells and then find out that they cannot service that property because you have water quality that is not suitable for development on private services. So the geoscience solution that we have for this is to develop an aquifer capability screening tool. This screening tool is a series of maps of expected groundwater quantity and quality that would help pre-screen development applications and help identify issues before development occurs or before you start dropping wells down. And this screening tool will also help support development, other development decisions such as zoning or infrastructure master plan, and we'll just move on. So this is our study area across Eastern Ontario. So we started the study in 2013. The study is part of the Ontario Ambient Groundwater Geochemistry Program. So that program was run, as this group knows, by Stu Hamilton. It's currently run by Laura Colgrove, and Laura will be talking more about this on day 2, I believe. So you can see in 2013 we started the study in the city of Clarence Rockland, and that is in the United Counties of Prescott and Russell, and this work was done with South Nation Conservation. The goal of the study is to collect data so that we can develop this screening tool. So we collect data at an even spacing across the study area. We moved our study first kept moving east in 2015 to the city of Alfred Plantagenet, and then in 2017 we moved to the city of Ottawa. The city of Ottawa is quite large. It's a large municipality, about 3,000 square kilometers, and we ended up dividing into 3 study areas, and I'll be talking about the east, the west, and the south. And you can see the 3 areas. The east we sampled in 2017, the west in 2019, and the south we sampled in 2022. So I'm going to be focusing on the City of Ottawa, not the other municipalities. But as I said, our goal was to collect high-quality geochemistry data from across our study area. So we used a 2-kilometer grid, and you can see the grid spacing on the figure. Our goal was to sample 2 wells, 1 or 2 wells from each grid. We're looking for 1 bedrock well from each grid cell and 1 overburden well from every other grid cell. And we don't get as many overburden wells because they tend to not be regionally, you just don't get the regional aquifer influence there. So at the start of each field season, the first thing we did was look for volunteers because we are actually sampling existing private wells. So we started off with advertising campaign, and you can see this is an example of a flyer that we made for 2019. We send this as we send the flyer out as a directed mail drop to everybody in the area. We also put up posters in public areas like the counselor's office and gas stations. We also did press releases, newspaper ads, social media ads, and to solicit volunteers. It was a very successful advertising campaign, and you can see the numbers listed on the bottom. So we had over 3,000 residents from the 3 study areas call in and want to be part of the program. Because of that, we were able to pre-schedule most of our sampling locations, which was really good, and it also creates buzz about this, and which is really beneficial in order for just teaching about general groundwater to the public. I don't remember. Let's move on. So our sampling program was all based on Stu Hamilton's Ontario Ambient Groundwater Geochemistry program. The sampling methodology was exactly the same. The sampling team would show up at a site. They would ask some questions from the well owner about their experience with water quantity, water quality. They take some measurements at the well, hook up to an untreated existing faucet, usually an outdoor tap, and if it was treated, the outdoor tap was treated, then it's usually at the pressure tank. They'd purge the system and then fill bottles, send those bottles for analysis. And you can see the list of parameters. We sampled for about 85 different parameters at each site. And here's just an introduction to the results. You can see our sampling, the distribution of all the wells sampled across this area. We have a good sampling distribution, and you can see the table on the bottom shows the number of wells sampled. So we sampled 799 wells throughout the entire area. I also wanted to bring up the background map is the bedrock geology. So we do see 3 distinct bedrock regimes sort of within this area. In the east, which is actually east of the Gloucester Fault, if you know the area, we get more of the upper Ordovician shales and shaly limestones. To the west, we do get sort of a Precambrian ridge, and we're also sort of in those middle Ordovician shales, shaly limestones. And to the south, we're getting more of the lower Ordovician Cambrian dolostones and sandstones. We also get a lot less of those sort of dug wells in the south area because we tend to get really good water quantity and water quality from the Paleozoic bedrock, and so there's less, people are less likely to put in sort of those shallow dug wells, which are more highly vulnerable to contamination or going dry. And finally, before I pass this over to Ant to talk about sort of the assessment of results and the development of the screening tool, I just wanted to put up a table showing the results. So these are a list of the parameters we're looking at. So remember, what we're developing is the groundwater screening tool. We're trying to develop maps where we would limit development. So if you exceed in a health-related parameter or a aesthetic parameter that's over a maximum concentration considered reasonably treatable, and you might not get your development approved, that's what we're focusing on. So you can see this is the table of values that we have. This is the table of parameters that had exceedances that would limit development. The numbers on the side in those columns show the number of wells that had exceedances. So we have the health-related, aesthetic, and then we have other parameters. The colors highlighted show sort of how we dealt with it in the ACST. If the ones that are blue, the coliform bacteria, the color, it was widespread. We couldn't link it to a geologic setting, so we just have one standard recommendation for that parameter across the study areas. The green are parameters where they were really localized, so we either had like a nitrate exceedance, but it was really just one well. It probably had some local impact, not really linked to a geologic environment, so we can't create a map as part of a screening tool. So those we didn't create as part of the screening tool, and the ones highlighted in orange, these are the ones that we could map it, link it to a sort of a geologic environment, and then develop the screening tool. So for those, we did fluoride, barium, chloride, sodium, DOC, and methane. And so now I'll pass it off to Ant, who will talk about the development of the tool.
Thanks, Tessa. Green for go. Okay, so in preparing, I found myself a bit tongue-tied, and Tessa, I hate to say it, but we renamed the Aquifer Capability Screening Tool. So it's actually an aquifer issue flagging tool, and I only sort of in jest say this because it just makes it easier to think about. So what it really is a list of potential issues, and the screening tool is just a GIS or a mapping tool that allows a planner to know if any of these issues exist or which of these issues exist at a certain location. And so on the slide, you'll see there's actually four different categories of issues. And there's one kind of quantity category for dug and drilled wells. And then there's three quality categories: the category for health parameters, the category for aesthetic parameters, and finally a category for dug wells, water quality and dug wells, or overburden wells. And we use those terms interchangeably. And then the map just shows the shape files that we ultimately produced for the Ottawa West study area. Speaking of the Ottawa West study area, here it is again. So this slide focuses on water quantity. Sorry, I've got to learn to look down here. So the Ottawa West, Tessa mentioned it, but it has a highly variable geology and hydrogeology. All of the rocks that are present in Ottawa, which go from Precambrian all the way up to Upper Ordovician, are present in the west. We have the pink Carp Hills, that's a big bedrock ridge. But basically, speaking of water quantity, essentially there's issues with water quantity in association with the Precambrian rock and with the thickest of the limestone, the middle Ordovician limestones. They're very shaly limestones. So we delineated, and you'll see in red, we have this area that's delineated. So that's an area of potentially low water quantity in drilled wells. And we delineated that based on the drillers. So the information for water quantity came from the water well records, and we delineated it based on the drillers' recommended pumping rates. But we also delineated it based on the depth of the wells, because we found that it wasn't enough just to use the pumping rates. We also needed to understand that in certain parts of this study area, drillers have to drill extremely deep to try to get water, and even when they do, they don't get very much of it. So that's how we came up with that polygon. And later in the presentation, I'll talk to you about a tale of two subdivisions, as I call it, and both of those subdivisions are smack dab in the middle of that area of potentially low water quantity. So in the east, we have, as Tessa mentioned, we have limited water quantity of variable quality in shale and shaly limestones capped by the Champlain Sea clay. So we have issues here of both quantity and quality. Specific to the water quality, so our job obviously was to try to incorporate geology into our understanding and incorporate geology into the way we delineated these problem areas. And for methane, that was quite easy. It was clearly associated with the shale. And the shale on the figure is shown kind of in purple hues. For the metals, like barium, fluoride, sodium, and chloride, we delineated those based mostly on they were much more present in the shale than in the shaly limestones. But also, we used a sort of, if clay was greater than 30 meters thickness, that helped us to delineate these areas. Something else of note on this slide is that we didn't just use the water quality data that Tessa collected as part of her studies, but the City of Ottawa has what they call the Ottawa Harvested Hydrogeological Information Geodatabase, or OHIG. So any subdivision report that's submitted to the city harvests the water quality information out of that, and that was made available to us and just helps to support the findings of the study. So for the south, we're currently engaged in assessing the data for the south study area. So I don't really have water quality or mapping to show, but I just wanted to show this cross-section. In the south, we have abundant water of generally good quality, and it's in a layered dolostone and sandstone. I wanted to show the cross-section because we did make, and hopefully you've seen the cross-sections that we made for all of the study areas. Again, we're trying to incorporate a good conceptual, hydrogeological conceptual model into our decision-making when it comes to delineating these areas, issue areas. The information for the cross-sections primarily comes out of the water well records. And if you look carefully, you can see the color-coded drillers, like observations of geology. They're quite good at picking out the difference between limestone and sandstone, but they're not good at picking out the difference between dolostone and limestone, which is not surprising, obviously. You can see the water found in the X's on the sort of lower down in the wells, and the static water levels are shown on this section as well. These maps are, or these cross sections are kind of like coordinated with the provincial overburden mapping and Paleozoic bedrock mapping. So for this part of Ottawa, what we're interested to find out is if we can see a difference in water quality and quantity between the shallow dolostone aquifer and the deeper sandstone aquifer. I think I forgot to mention earlier that planners may find it a little bit too much to look at a different area for fluoride and barium and DOC. So we kind of, relatively early on in our involvement, my involvement in this work, we kind of came up with doing a catch-all. So for basically any kind of water quality issue in a drilled well, for example, an exceedance of a maximum allowable concentration, or sodium chloride or DOC above an aesthetic objective, we were interested in delineating where we would see those kinds of issues. And the map shows basically from the east, the results from the east and the west, and obviously we're going to add the south. So this screening has been applied to all the Eastern Ontario ACSTs, and as mentioned, the plan is like just going to one layer for water quality. They still have to go and look about water quantity in a separate layer. So what I find interesting about this map is looking at the polygons, the shapefiles that we've delineated. They kind of imply a certain precision because of the, tight corners and things like that. And that precision, obviously, we want it to reflect geology, but we also want it to reflect the interesting and important data that Tessa has collected from groundwater quality. So I would say most of the precision comes from the data, which is just another way of saying what everyone always says, which is we need more data. And hopefully we've also done a good job incorporating the geology. And clearly these, but it does kind of point to the challenges of making a defensible screening tool for the use by the City of Ottawa. This slide, which is my last slide, is just sort of an example. So the purple is this area of potentially poor water quality in drilled wells. And if you look carefully, you'll see there are 2 existing subdivisions, but let's just pretend that those didn't exist and developers were coming to the city to want to create or to build a new subdivision. Without the screening tool, there would really be not a lot of information about anything for the planners to help the developer with their studies. And so really that's kind of the driving force behind the tool. For the one on the right that's inside the purple area, both of these areas, as I mentioned, are in areas where there is poor water quantity. But for the one on the right, we have potentially problematic fluoride, sodium and chloride, and DOC, as well as color and bacteria, which are kind of widespread throughout the area. The subdivision on the left is outside of the area, the purple area, and it really doesn't have any of those water quality issues. So I think that's it for me, and I'll pass it back to you, Tessa.
Yes, so just in summary, this really was just a practical application of geoscience to develop this pre-screening tool to help development planning at the municipal level. It's also important to note that this is just a pre-screening tool. This does not negate the actual on-site studies to be done. So if you're in an area that has no issues, you might still have issues. We're just trying to pre-screen. In doing the study, we are sort of advancing that understanding of Ottawa's complex geology and hydrogeology. The project itself is built on these collaborative partnerships, and big thank you to all of the project partners, especially the Ontario Geological Survey, and all of the students that helped with this. We actually ended up getting 4 master's students who had their thesis in something to do with this Eastern Ontario studies with the University of Ottawa. And as I mentioned before, it really really supported that public awareness about private wells. We had over 3,000 people call, plus the field team would, in those grid cells where no one had called, you're knocking door to door, you're outside, you're doing the work with landowners, you'd see a well without a cap and you'd tell them you should cap it. So it really encouraged the public to become more aware as well. So thank you very much.